Alright, welcome back to Honors Topics in Physics. Torque and center of mass is what we're talking about. So the first question is, what causes an object to change its rotational speed or change its rotation? And that is starts with the letter T, torque. How do you create torque? Where you apply a force perpendicular to the lever arm. When does a force create no torque? And that's if it's got no lever arm. Okay, so if I were to ask you a question here, which of these arrow forces creates more torque? Okay, well, the answer would be neither. They both create zero torque. Any force that points through the axis of rotation, or the axis of rotation, creates no torque. Both of these point through the axis of rotation. Neither will cause rotation, and so they create neither. Okay, so here we've got a meter stick that's balanced on a triangular pivot point. So is there going to be a net force acting on this meter stick? Okay, these are the forces shown on it. We've got a force of gravity equals mass times gravity. We've got an equal, we're showing it with hash marks. Upward force by the normal force by the pivot point. And so the answer is there's not going to be a net force because these forces are going to cancel. Okay. Is there going to be a net torque? Okay. Well, both of these forces point through the pivot point. The pivot point would be this point of contact here. So if they are in line with the pivot point or the axis of rotation, same thing here. Then neither of them are going to create torque, and this meter stick is going to be balanced. So basically, if you put the center of gravity, shown in the red dot here, which is in the middle of a symmetrical meter stick, above the pivot point, or below it for that matter, somehow, then you're not going to create torque, and everything is going to balance. Okay. If I move the fulcrum over, okay, and then is there a net force now? I still have the normal force up, and that's balanced by the force of gravity down, as shown by these hash marks. So the net force on this meter stick is going to be zero. Is there going to be a net torque? Okay, well, this normal force is still in line with my pivot point, so it's not going to create any torque. However, this force of gravity, which notice I've located at the center of gravity. You always put the force of gravity of an object at the center of gravity, which is typically in the middle, unless we're doing a lab, in which case the meter sticks are not uniform. They have like a knot somewhere, which moves the center of gravity off the center point. So we are going to create torque, and what's going to be the lever arm? Okay, it's going to be this distance, this horizontal distance between the pivot point and the force. So remember, what you do is here's the axis of rotation. You draw a line through the force, and then you look at the perpendicular distance from that line to the axis of rotation, which is going to be this little bottom of the meter stick right here. So this is going to create torque, and it's going to create clockwise torque. So this is not going to balance. Okay, we've already answered those questions. So here we've got a 6 meter long board which has a weight of 800 newtons. If the fulcrum is placed 2 meters from one end, what is the torque on it? So it's very useful when you're doing these problems, these types of problems, to draw a picture and label it with distances to keep yourself from getting screwed up. So here I've drawn my board, and here I've put the fulcrum 2 meters from one end. The next useful thing that you're going to want to put on this is the center of mass, center of gravity, which we're going to put at the center of the board because it doesn't tell us any differently. On the word problems, we're always going to put the center of mass at the middle of an object. So because the board is 6 meters long, I've put it halfway to the other side. Now it's not drawn perfectly, And it doesn't have to be drawn perfectly, as long as you know what the dimensions are. So I've drawn this 3 meters from one end, okay? And the question is, what's the net torque? Well, torque is equal to force times distance. The force here is 800 newtons because that's the weight of the board, and I've got that labeled, which is also you need to have labeled on your diagram. And the distance here is the lever arm distance. It's the distance from the force to the pivot point. Okay, so it's this distance right here, from the force to the pivot point, which, as seen in my diagram, is a distance of 1 meter. Okay, so again, the diagrams help simplify the picture a little bit. Okay, and so the torque would be 800 Newton meters clockwise. Okay, so here's another example. What torque does gravity create on a 0.45 kilogram meter stick, which is supported at the 15 centimeter mark? So I've already got kind of a picture drawn here, but I'm going to go ahead and redraw this. So we've got a 0.45 kilogram meter stick, and we're supported at the 15 centimeter mark. So again, we're looking for force and lever arm, force and distance. And the distance is the distance from the force to the fulcrum, okay, which is at the 15 centimeter mark. So the force is the force of gravity. Now, I gave you the mass. So what we need to do is multiply the mass times gravity. So 0.45 kilograms times 9.8 equals 4.41 newtons. So the torque here is equal to that 4.41 newtons times the lever arm distance. Now, the fulcrum, it said, was at the 15 centimeter mark. Okay, we know that the center of gravity is going to be at the 50 centimeter mark. Okay, unless told differently. And so that's where we're going to put our 4.41 newtons right here. Now the lever arm distance is the distance from the force to the fulcrum, which is 35 centimeters. Now centimeters isn't a proper physics unit when we're working problems typically, so we're going to convert that into meters by moving the decimal place twice and getting 0.35. Okay, so when we multiply that times the force, we get that our torque is equal to 1.54 Newton meters, and that is again clockwise. Okay. This torque thing also applies to when objects fall over. We said an object won't fall over as long as its center of gravity is over its base of support. So here we've got a book or whatever, and we've got the table is flat and the center of gravity is directly above the base of support. This is like a wrench where the force is being applied straight down into the axis of rotation. Applying a force like this isn't going to cause a wrench to turn. Okay, having everything set up like this isn't going to cause the book to turn or fall over. So that's how they're balanced. However, if I tilt things a little bit, okay, so here's my book, and we draw a line straight down from the center of gravity. Okay, we see it's no longer over the base of support. Okay, so this is going to fall over. Similarly, if we go to my wrench, and here I'm applying my force here, okay, applying my force here is going to cause some rotation. It's going to cause some rotation in the counterclockwise direction. There is going to be lever arm, and the lever arm distance is going to be that perpendicular distance from the force. So it's going to be the horizontal distance from the force. So it'd be this distance right here. Okay, this torque, this lever arm distance would be the distance from this corner to the where the force would come down. Okay, and that's going to be my lever arm here. Okay. Oh, and here we've got it shown a little bit better. Oh, okay. I wish I'd known that. I put that in there. So these are my lever arm distances shown. Okay. When an object is tilted over more, okay, there's more torque available to cause it to rotate or fall over. So here, this is my lever arm distance here. Okay, it looks to be, well, let's say about a centimeter. When I tilt it over more, this is my lever arm distance here. Okay, and this looks like more like 2 or 3 centimeters. So I get more lever arm, I'm going to get more torque, and it's going to be falling over more. Okay. Gravity also exerts torque. When you bend over and you do not have your butt stuck behind you, if you're if you're standing straight up and you bend your body straight over, your center of gravity is somewhere off your body, somewhere about right here. So this is your legs and your feet, and this is your chest and your head. And so this force at your center of gravity, remember we always put the force of gravity at the center of gravity or center of mass. Your base of support is your feet right here. And if your force of gravity is not over your base of support, you're gonna fall over, and that's because you're gonna have some lever arm, which is gonna create torque. It'd be this little distance right here. Okay. Would this object fall over? Okay. And the answer is no. Okay. If I draw a line straight down, okay, remember you got to draw these lines straight down. You can't draw them at an angle. There's always a couple on the test where they do this and they draw them like this. Okay, and the answer is yes, it'll fall down. But the answer is no in this case, because I have to draw that line straight down, and it's over the base of support. It's not going to fall over. Okay. So going back to a little bit of review from a while ago here, a net force causes an object to do what? Okay. A net force, it starts with an A. A net force causes an object to accelerate. Okay. A net torque causes an object to do what? Okay. A net torque causes an object to rotate. Okay, so we're gonna there'll be some multiple choice questions along these lines, and they're not meant to be hard. You just got to know how to play the game. So when a football is kicked and it's spinning in the air, the axis of rotation, okay, goes through the center of mass, meaning it's spinning around its center of mass, which is what things do. Okay, the center of mass shown in red, and it's spinning about that point. So it's spinning about its center, basically. Okay. Could you kick a football so that it will simply take off, but it won't rotate? Okay, so could you kick a football in such a way where it just it doesn't rotate, it just takes off without rotating? Okay. And the answer is yes. Okay. If I kick this football with a force that's applied like this, so my foot's over here, and I'm kicking this football directly through the center of mass, center of gravity, okay, will it accelerate? Okay. The answer is yes, it'll accelerate because there's a net force. There's a net force because I'm kicking it. Okay. If I kick the football, of course it's going to accelerate. It's going to take off. Okay. Will it rotate? Okay. The answer is no, because the force points through the axis of rotation, through the center of mass, center of gravity, so it will simply take off like this. Okay, so it'll just take off like that. Okay, what about this? If I kick the football down a little bit, okay, so now I'm down here. Will this football accelerate? Yeah, because there's a net force. Okay. Will it rotate? Okay. Am I kicking it through the center of gravity, center of mass? And the answer is no. So it'll take off and spin. Okay. So it'll accelerate and rotate. So that's an example when you do both. Let's say I kick a football like this, kind of upwards and at an angle. Will it accelerate? Okay. Yeah, sure, it'll accelerate. Because I'm kicking it again. Okay. Will it rotate? Or there's a net force. Okay. Will it rotate? Okay. And the answer is, looking at this force, it goes through the center of mass, center of gravity, so it's not going to rotate because there's no lever arm. Okay, any force through the axis of rotation, which is through the center of mass. Center of mass is the axis of rotation here. Okay, any force through the axis of rotation causes no rotation, just like what we talked about before. Okay, let's see, let's skip that part. One thing I want to point out about a ball, if I were to like let a ball go down a hill, what force causes it to rotate? Because the ball will rotate as it rolls down a hill. The normal force, okay, is perpendicular to the surfaces at the point of contact. Okay, the force of gravity is at the center of gravity. Okay, and the force of friction is at the point of contact, upwards from the slope. Okay, so as it's spinning, okay, it's going to rotate about its middle, which is also through the axis of rotation, which is through the center of mass, center of gravity, in this case. And so will the force of gravity cause it to rotate? No. Okay. The force of gravity is pointed through the axis of rotation, so it will not cause it to rotate. What about the normal force? Okay. The normal force, this is going to also be pointed through the axis of rotation here, like so. And so that's not going to cause it to rotate. What about the force of friction? Will that cause it to rotate? Okay. And the answer is yes. Okay. And what's its lever arm? Okay. It's the radius of the ball or whatever it is. So without friction, a ball would simply slide down a ramp. Okay. You have to have friction in order for the ball to rotate as it rolls down a hill. Okay. All right. So in order for an object to remain completely stationary, in other words, their velocity is zero, they're not rotating, they're not doing anything, such as these guys here, these five gymnasts, and they're in what's called equilibrium. They're perfectly stationary. In order for that to happen, two conditions have got to be met. Okay, they're not accelerating, so all the forces have got to cancel. Okay, and they're not rotating, so all the torques have got to cancel. So that's the name of this game. Do the forces cancel? Do the torques cancel? Alright. So here we've got a bar that's spinning. So this is my bar or book or whatever you want to think it is. It's in outer space. The center of mass is in the middle of it. So that'll be its natural axis of rotation. There's no gravity because we're in outer space, so these are the two forces that we're applying to it through rockets or whatever we're doing here. So the question is there a net force on the object, aka does it accelerate, and is there a net torque, aka does it rotate? Okay, so the first step is there a net force on the object? Well, I've got 100 newtons to the right, and I've got 100 newtons to the left. Okay, so those forces are going to cancel, so it's not going to accelerate. Okay, is it going to rotate? Okay, well, let's say that the whole thing is 2 meters, so this is 1 meter from the axis of rotation up and 1 meter from the axis of rotation down, just to come up with some numbers. So in this case, I've got 100 newton meters of torque. What's the direction of this torque? If this is where this thing is pinned, if this is where it's rotating about. Okay, it's going to be rotating in the clockwise direction. Okay, so 100 newton meters clockwise. What about this force right here? This is creating torque because, again, this is my axis of rotation. It's not pointed through it. So what's the direction of this torque? It's also going to be 100 newton meters because it's 1 meter away from and again, I just made up that 1 meter, 1 unit away from the center. Okay, what's the direction of this torque? Okay, if I have this pinned in the middle. Okay, if you picture this as a piece of cardstock or a notebook card, and you put a pin right in the middle. which way is this force going to cause it to rotate? Well, it's going to cause it to rotate like this, okay, which is in the clockwise direction. Okay, so this was 100 Newton meters clockwise, and this was 100 Newton meters clockwise. So my net torque is 200 Newton meters clockwise, so it's going to rotate. So this thing with these two forces applied like this, all this this bar is going to do is just spin around in the same place. Okay, that's what That's what happens if you've got no net force, but you got a net torque. Okay. What about this one here? Will this object accelerate? Will this object rotate? So again, and this time I've got the center of mass marked. It's in the middle, and so I've got 100. Let's consider this distance 1 meter just to make the numbers easy to work with, and 1 meter down, just like before. So in this case, I've got 100 Newton meters of torque. What's the direction of this force's torque? Okay, it's going to be like this. Okay, and that's going to be clockwise. Okay, so we've got 100 Newton meters clockwise. Okay, and here we've got 100 Newton meters. And what's the direction of this torque? Well, it's going to cause it to rotate the opposite way. It's going to cause it to rotate like this. So it's got 100 Newton meters of counterclockwise. Okay, so these torques are going to cancel. So this is not going to rotate. Okay, I think I forgot to mention if it was going to accelerate. We've got 100 newtons to the right, 100 newtons to the left. So it's not gonna accelerate either. So this metal bar or this object is in equilibrium. It's not going to accelerate and it's not going to rotate. Okay. Let's see. Will this object accelerate or rotate? So here again we've got our center of mass marked in the middle. So here we've got 100 newtons to the right and 100 newtons to the right. Okay. So are these forces going to cancel? No, they're going to add. So so this object is going to accelerate. Okay, is this object going to rotate? Well, let's see. So this is the same force we've had at the same location. So it's going to be 100 Newton meters clockwise for the same reasons as before. Okay, let's see. Is this torque from this force down here? Is it going to add or is it going to cancel? Okay, it's going to be the same amount because it's at the ends, and this is the middle. This is my axis of rotation. So it's 100 Newton meters. Will this be in the clockwise or will it be in the counterclockwise direction? Okay, so this force is going to cause it to spin like this in the counterclockwise direction. So this is 100 Newton meters of clockwise, and this is 100 Newton meters of counterclockwise. So these torques are going to cancel. So it is not going to rotate. So this object will accelerate but not rotate. So it'll just take off. Okay, well, it would just take off to the right without spinning, kind of like the football that didn't spin, it just took off to the right. Okay. What about this? Okay, now I added a 200 Newton force in the middle. Okay, now will this accelerate? Here I've got 100 newtons to the right, and I've got 100 newtons to the right, and I've got 200 newtons to the left. So those forces are going to cancel. Okay, so this object will not accelerate. What about rotating? Okay, in the example before, these two forces canceled. Okay, so we don't have to worry about them causing torque and causing rotation. Let's look at this. Will this object cause torque and rotation? Okay, well, this force right here points right through the axis of rotation. So it's not going to create torque. It's got no lever arm. So it's not going to cause rotation either. So these two forces cancel, okay, and this force doesn't create torque. So this object will not rotate. So this object will be in equilibrium. Okay. Let's see. will this object accelerate? Well, it's got 100 newtons to the right and 50 newtons to the right, and so this will accelerate. Will this object rotate? Okay. Well, here we've got, from the same reason as before, we've got 100 newton meters of clockwise. Okay. Now I've got 50 newton meters of counterclockwise. Okay. So these forces don't cancel. I'm going to end up with some extra force in the clockwise direction because this is a bigger torque. So this object will both accelerate and rotate. Okay. What about this? Will this object accelerate or rotate? Okay. So here we've got 100 newtons to the right and 50 newtons to the left. So I'm going to end up with 50 newtons of net force to the right. So it will accelerate. Okay. And here I've got 100 Newton force that let's say it's halfway to the center of mass. So a half a meter, a half a unit. So this is going to create 50 Newton meters, 100 times 0.5 meters. Okay. 50 Newton meters in the clockwise direction. Okay. So determining if it will rotate. What about this guy? Well, this is going to create 50 Newton meters. Okay, it's got 50 newtons in 1 meter. Okay, what direction is this going to be? Okay, so this is going to be in the clockwise direction also. So these forces don't cancel, they add. Okay, they're going to cause it to spin. Alright, so this will rotate. So it'll both accelerate and rotate. Alright. So let's say we have a 150 Newton person who stands in the middle of two scales on a board. What does each board read? So let's work this example. So we're kind of switching gears here from multiple choice problems to written problems. So that's kind of what we're doing now. This would be a written problem on the test. Okay. So if a person stands in the middle of both boards, and these are scales here. And the board is weightless, so we're not worried about the weight of the board. He's 150 newtons. Each of these scales are going to read 75 newtons because he's in the middle. Okay. If they were to walk to the right, okay, this scale would start to read more, and this scale would start to read less. But in the middle, they read equal. Okay. And so do the forces cancel? Yes, because nothing is accelerating. Okay. Do the torques cancel? Yes, because nothing is rotating. So I know that what we've been learning about would apply to a situation like this. We're just not going to do it right now. Let's look at another example. So let's see. Where should a person stand? So this is a 150 Newton person again. So that one scale reads 30 newtons. Okay. So we don't know the length of the board. We're not worried about it right now. We'll just look at the fraction of the way over. So we know that they're going to be further away from this 30 Newton scale because it's reading less than half of their weight. Okay. So what does this scale have to read? Okay, over here. Well, if the forces cancel, okay, and I've got 150 down, that means I need 150 up. Okay, so I've got 30 newtons here, so the remaining distance is going to be, the remaining force is going to be 120 newtons. So the scales have to add up and read their weight, basically. Okay, alright. Now the torques also have to cancel. And so what we're going to say is this is 30 newtons and this is 120 newtons. So the torques have to cancel. So this force is 4 times the force of this one. Okay. And by the way, if we can consider the person the center of mass or the axis of rotation, this would be creating or trying to cause clockwise torque. Okay, and this would be causing the reverse counterclockwise torque. So the torques have got to cancel just like we did before. So this should actually be pretty similar to what we've seen before, where it's this fraction of 4D or 1D and 2D, that kind of thing. So if this is 4 times the force, okay, then this has to have 4 times the lever arm. So I'm going to call this distance D, okay, and this distance 4D, okay. So when I multiply these two together, D times 120, I get 120D, okay. 4D times 30, okay, gives me 120D. So everything balances out. The torques are going to cancel, okay. So this distance right here is 4/5, okay, because I've got a total of 5 D's, and this is 4 of the way over, okay, and there's remaining 1 D over here. So this is 4/5 the distance over. So if this was 100 meters per se, then this would be 80 meters over, and this would be 20 meters the rest of the way. Okay? What if a person stands 1/3 of the way from one scale? What do both scales read? Okay? So person stands 1/3 of the way over. That means we've got 1 unit of D here, and we've got two units of D here. Okay? And so what would the scales read? Okay. Well, if this guy has one unit of distance, and this has 2 units of distance, this needs to have 2 units of force, and this needs to have 1 unit of force. Okay, so that's one way you can think about it. The other way you can think about it is if this is 1/3 the distance, okay, and this is 2/3 the distance, this needs 2/3 the force, and this gets 1/3 the force. So the fractions just kind of flip like that. So if this needs 2/3 the force, 2/3 of 150 is going to be 100. Okay. So this scale reads 100, and this scale reads the remaining 50. Okay. So that was a little bit of a longer notes for the day. Sorry about that, but I tried to go a little bit slower. So go ahead and work on the worksheet in the module, which should be Torque and Center of Mass worksheet 8.5.